we're going to do a overview of Chapter 2 from the Burge textbook. So Chapter 2 has 8 sections in it. It begins by talking about atomic theory and the structure of the atom. Then it goes through some simple arithmetic of the structure of the nucleus. Then a brief overview of the periodic table, and then some discussion of atomic mass. And then a relatively comprehensive view at naming what are called binary compounds. So let's begin in this overview by talking a little bit about the history. The idea of atoms goes back a long ways, goes back thousands of years. The idea that what we observe in the universe, the matter that we hold in our hands or our bodies, our cells, are made up of tiny particles that are so small we can't see them with the naked eye, is the idea of an atom. So the idea is very old. But what we do is we'll talk about the modern theory of atomic theory. So we begin really with John Dalton. John Dalton did some experiments and came up with what we might consider a modern theory of the atom, saying things like elements. So for example, hydrogen is an element or oxygen is an element. That those elements are composed of really, really small particles called atoms. And so every atom of the same element is identical. So you can't have one type of hydrogen and another type of hydrogen. You can't have more than one type of oxygen. Every oxygen atom is identical. And that compounds are really combinations of atoms from two or more elements. So for example, water is a combination of the element hydrogen and the element oxygen. And then what happens is during a chemical reaction, the atoms are rearranged in such a way that they become new substances. So for example, in this figure here, figure 2.2, it's showing a reaction occurring. So there are diatomic elements there, the red ones, reacting with monatomic atoms and a monatomic element and forming a compound. And so it's not that anything's happening to change the red atoms or the gray atoms and destroy them or create new ones. They're merely just recombining in some fashion to make a different substance. Okay. So again, reminding ourselves a little bit about the models that we use. In figure 2.3, the illustration of the law of multiple proportions is this idea. If we take a look at carbon dioxide has a carbon atom at the center and two oxygen atoms attached to it. So the red atoms or the red balls are oxygen and the brown or black one is carbon. So that's carbon dioxide. And if you look at a carbon monoxide has one carbon and one oxygen in the compound. It's a 1-to-1 ratio. So these proportions, they're showing you these proportions. If you take a look at it, CO2, carbon dioxide, 2 oxygens for every carbon, CO, 1 oxygen for every carbon. So make sure you go through the sample problems and the practice problems and the checkpoints for that. So really all we're looking at here is an introduction to the modern theory of atoms, atomic theory we call it. So let's go on to the next section here, which is the structure of atom, which is very interesting. This is work that's really quite a breakthrough, quite a development in the history of science. The idea that we could take these things that are so small and invisible to the eye and actually figure out what they're made out of. It turns out that the atomic theory is that we discussed in section 2.1 has an error in it. And we'll see what one of those errors is as we move along. But in any case, there's a little bit of history here and a little bit of discussion of the types of experimentation that went on. The discovery of the electron is given here. This picture here in figure 2.4 is a cathode ray tube. cathode ray tube. That technology was used throughout the 20th century for television sets. Essentially, electrons are accelerated toward a glass screen, and when the electrons collide with phosphors on the surface, the inside surface of the glass, light is produced, and that gives you a television set. So the electron was a particle that was discovered, and one of the breakthroughs was to figure out what the mass and the charge was. So the charge of an electron is given here as negative 1.6022 times 10 to the minus 19th. C is coulombs. And the mass is given over here on the right as 9.10 times 10 to the minus 28 grams. So quite a development to figure out what the electrical charge in coulombs is and the mass of the electron in grams here. And notice that we do give it a charge of negative. The electron is believed to be a negative charge. Experiments led through radioactivity, the decay of certain types of atoms that are unstable. It's called radioactivity. Alpha particles and beta particles and gamma particles were discovered historically. The proton in the nucleus of the atom was discovered through the gold foil experiment. And then finally, everything was kind of put together to give us the idea of what the atom is. So I'm going to come over here to figure 2.9. If you take a look in figure 2.9 on the left, there's a picture or a depiction of the atom. That little dot in the center is essentially representing the nucleus, which is where protons are, which are positively charged, and neutrons are, which have no electrical charge, no net electrical charge in any case. And then the whole space is the size of the atom. It turns out that the electrons are occupying that vast space around the nucleus, much, much larger than the nucleus. If you take a look at the difference in size, it's 10,000 to 1. The diameter shown here for the size of the atom, which is the space occupied by the electrons, is 10 to the minus 10 meters. That's an angstrom. And the size of the nucleus is 10 to the minus 14 meters. That's 1/10,000th the size of the atom itself. So the nucleus is tiny, 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 and that's where the protons and neutrons are. And in table 2.1, some information is given. The mass and the charge unit of these particles. So the electron has a mass, shown a little more precisely here, 9.10938 times 10 to the minus 28 grams. The proton, even though it's also very small, it's much larger than that of the electron. 1.67262 times 10 to the minus 24 grams. That's much, much larger. It's 2,000 times larger. So one proton has the same mass as 2,000 electrons, or approximately 2,000 electrons. Then you have the neutron. If you take a look at the mass of the neutron, it's almost the same as a proton. It's much, much larger than the electron by, I think the actual numbers are around 1,800 times larger than the mass of the electron. Those particles, the proton and neutron, are very, very dense compared to the electron. They weigh a lot. If you look at the electrical charges, experimentally what has been shown is that the proton has exactly, as far as we can tell, it's exactly the same charge as the electron, only the opposite charge. It's positively charged. The neutron has no net charge. Now, what is done is something called the charge unit over here on the right. Because the electron has the same charge as the proton and the neutron has no charge, it's convenient to normalize it, to scale it, and just to say, look, relative to the other particles, the electron has a charge of -1, the proton has a charge of +1, and the neutron doesn't have any charge, so it has a charge number or charge unit of 0. So if we were trying to calculate forces or energies, we would use the actual charge in coulombs, 1.6022 times 10 to the minus 19. But for counting up charges, so for example, let's say an atom has 10 electrons. What's the charge of those 10 electrons? Well, we would say each electron is -1. There's 10 electrons, so that's -10. That's more convenient, but we wouldn't use that for actual calculations. We would just use it for giving us an idea of how many particles there are and how much charge there is relative to another atom. So that's section 2. Taking a look here It doesn't look like section 2 has any practice problems or anything like that, so that's the nature of that one. Let's move on to section 3. This is where you'll do a little bit of the calculations here. These are simple calculations. Practice them. They're really, really easy. And you know, unlike some of the issues you might have been dealing with in chapter 1 with precision and accuracy and dimensional analysis, this is really easy stuff. So learn it quickly. The atomic number Z is the number of protons in one atom, in the nucleus of an atom. So if you have an atom with 10 protons, the atomic number is 10. Now, an atom has the same number of electrons as it has protons. It's evenly matched. So if you know that the atomic number is 10 protons, you also know that that atom has 10 electrons. Now, in terms of mass, we had the mass in the previous section, 2.2, in grams. Here what we're going to do is we're going to call something the mass number. And the mass number, A, is just the number of protons plus the number of neutrons in the nucleus of one atom. So if an atom has 6 protons and it has 6 neutrons, that's 12. The mass number would be 12. And we represent this through a notation called isotopic notation. So right here in the middle of the page, isotopic notation, X is the symbol for the element. So that could be an O for oxygen or an H for hydrogen. Z is written as a subscript down on the bottom on the left, and that's the atomic number, so that's the number of protons. So if it were oxygen, it would have 8 protons, so the Z would be 8. And then the mass number is the number of protons and the number of neutrons added together. That's going to be a whole number. So we're not going to have half of a proton or a third of a neutron. The mass number is a whole number, as is the atomic number. Now, it turns out that Dalton's theory, his hypothesis, was wrong at least in one way, which is it turns out there are different types of atoms for a specific element. So hydrogen, for example, is known to have at least 3 types of atoms. One is dominant in nature. It's 99% of all the hydrogen in the universe is hydrogen 1. So the one on the left here, H11, it has 1 proton. It has a mass number of 1. What that means is it doesn't have any neutrons, because if the mass number is neutrons plus protons and there's 1 proton, remember the subscript is the number of protons, that's the atomic number. If there's 1 proton and the mass number is also 1, that means there can't be any neutrons. It's got to be 1 plus 0. So hydrogen 1, it's often referred to, the one on the left, is the most dominant form in nature. The one in the middle, called deuterium, has 1 proton and 1 neutron. So 1 proton, that goes on the bottom, that's the atomic number, Z. And then the mass number is proton plus neutron, so that's 1 plus 1, which is 2. That's the mass number that goes on the top. And then the one on the right, tritium, 1 proton, 2 neutrons, gives it a total number of 3, a mass number of 3. Okay? Every element in nature has at least 1 isotope. Uranium is an important element for various reasons. Nuclear power, nuclear weapons. So uranium comes in more, there's more than 2 isotopes of uranium, but these are the 2 commonly ones found in nature. Uranium has 92 protons, so it has an atomic number of 92, that's written on the bottom. There are 2 isotopes written here, 235 and 238. So from that, you know the mass number is 235 for the one on the left, mass number is 238 for the one on the right. So from that information, you could find out how many neutrons each isotope has. Because remember, the mass number is the total, protons plus neutrons. So if you know the protons is 92, and you know the total is 235, then the number of neutrons would be 235 minus 92, and that's 143. So the one on the left, uranium-235, has 143 neutrons. The one on the right, uranium-238, has 3 more neutrons. So isotopes differ in the number of neutrons. So the one that has more neutrons is heavier, the one with fewer neutrons is lighter, but they're the same element. Chemically, they behave very similarly. So uranium-235 and 238 are pretty much the same chemically. Very, very minor differences, but they do have different weights because the neutron has weight. So if one has more neutrons, it weighs more. And then there's some sample problems you want to take a look. Again, these are really easy calculations to do, so try them all, rip through them, practice them, and you'll have that down. Periodic table. We're going to look at that really quickly here. The periodic table, Right now it is believed that there's 118 elements that have been discovered. Some of them are unstable. Many of them are unstable, and so you don't find them in nature. By the time you get up to 92, 92 is pretty much the end point in nature. Anything above 92 is just so unstable you don't really find it in nature, but it can be made in laboratories. So 93, 94, 95, 96, so forth, all the way up to 118. Now, I'm not going to go over the details of this right here, but I'm going to make a few points. One is, be careful comparing the periodic table to isotopic notation, because there's an opposite issue here, which is in isotopic notation, the atomic number, the number of protons, is written in the bottom, right? It's written at the bottom of the symbol. But in the periodic table, the atomic number is written above the symbol. So for example, H, the one in the top, that's the atomic number there. So it's a different notation, it's a different symbolism, so be careful about that. The atomic number is written above the symbol of the element, and some periodic tables will write out the whole name of the element, aluminum, A-L-U-M-I-N-U-M. Some will not. This one does. No, I know. Okay, so in this particular periodic table, the metals are shown in green, and if you take a look at the table, most of the elements in nature are metals. The ones in blue are nonmetals, so there's some nonmetals on the right side, and then the ones that are orange are in the middle on the right, sort of separating the metals from the nonmetals. Those are called metalloids, and those ones have properties that are sort of in between. Now, you think about what's the difference between a metal and a nonmetal. Metals tend to conduct electricity really well. They conduct heat really well. Nonmetals do not. Metals can be stretched into wires. That's called ductility. They can be pounded. That's called malleability without shattering. Nonmetals tend not to do that. Metalloids are sort of in between. They do conduct electricity and heat better than nonmetals, but not as good as metals. Okay. Read through some of the discussion there of halogens and noble gases and all of that. Nice little picture here, the bringing chemistry to life distribution of elements on the Earth. That's kind of an interesting thing. And then do the checkpoints. Okay. Next section, 2.5, the atomic mass scale. Now you're going to get back into calculations here. We're going to figure out what the atomic mass, not atomic number, but atomic mass is based on a scale here. So the atomic mass unit in AMU is defined as the mass that's equal to 1/12 the mass of one carbon-12 atom. So that's just a definition. It's the way we think about it. It turns out that definition has changed recently, but we'll go with what it says here in the textbook. Essentially, the issue here is the following. Each isotope of a specific element has a mass. The more neutrons an atom has, the more mass it has, the greater the mass is. So since each element in nature has more than one isotope, it's a mixture of different masses. Oxygen with 8 neutrons weighs less than oxygen with 9 neutrons. So if you find oxygen in nature and there's some of each, oxygen 16 and oxygen 17, it's going to be an average when you measure it. So we have to take that into account here. So the calculation is shown here in the middle of this page. It turns out that for carbon is the example that's given here, 98.93% of carbon is carbon-12, so it weighs exactly 12 AMU. And then 1.07% of carbon in nature is, or at least on the Earth, is carbon-13, and it weighs more, 13.003355 AMU. So if you were going to measure carbon in nature, what you get is a mass that's an average of the two. And so you get this average here, which is 12.01 AMU, and that's the atomic mass. It used to be called atomic weight, but we refer to it now as atomic mass. Here's a discussion of how atomic mass is measured using what's called a mass spectrometer, so you can look that over. And then this calculation here in sample problem 2.3, this is an important type of calculation, so I encourage you to look that over for oxygen and do that one. Look over the problem. It's called a weighted average. And do the practice problems for this one, and of course the checkpoints as well. There's really one type of calculation in this section, and that's how you get the atomic mass. We're trying to figure out how much these atoms weigh. Okay? So let's take a look at now section 6, which is ions and ionic compounds. So ions and ionic compounds are important because many of the substances that we find in nature are made up of ions. They're not made up of atoms. An atom is a neutral particle. In an atom, the number of protons is equal to the number of electrons. So the charge of the protons cancels the charge of the electrons. So overall, the particle doesn't have any net charge. But ions can have varying numbers of electrons. And so they can have a different number of protons than they have electrons. So that gives them an electrical charge, and that gives them very interesting properties that neutral atoms don't have. So for example here, the sodium atom has 11 protons, 11 electrons. How do we know that? Well, sodium is element number 11. So we would just go back to our periodic table and look up sodium and see, oh, it's atomic number 11, so that means it has 11 protons. It also means it has 11 electrons. But it turns out in nature there's something called the sodium ion. In the sodium ion, one of the electrons has been removed. So it has 11 protons still, but now it only has 10 electrons. So it has more positive charge than negative. So it is what is called a cation. A cation, C-A-T-I-O-N, is a positively charged ion, and the sodium ion is charged. It's cation. Chlorine, on the other hand, with 17 protons and 17 electrons, Cl, chlorine has a tendency to gain an electron and have 18 electrons instead of 17. So now it has more negative charge than positive. So it is now a negatively charged ion, which is called an anion, A-N-I-O-N, anion. So chloride is an anion. So if you take a look at the periodic table here, the metals, interestingly enough, are all positively charged. They're all cations. That means they have more protons than electrons, which means that they lost electrons. Whereas on the right side, in the blue, the nonmetals, they're all negatively charged. They've all gained electrons. So they are anions because they have more electrons than protons. Remember, electrons negative, protons positive. So if you combine these particles, a metal with a nonmetal, they form what is called an ionic compound, and they are attracted by what's called electrostatic interactions. The cation, the metal ion, is positively charged. The nonmetal anion is negatively charged. Positively charged particles are attracted to negatively charged particles, so they combine in small ratios, 1 to 1 or 2 to 1 or 1 to 2, in order to neutralize each's charge. So if you take a look here, here are some examples of iron, Fe2+. That's called the ferrous ion. That is a +2 ion. Now that's an old nomenclature, us and ik. You'll see it out there. We don't use it very often. But what we would say is that iron comes in 2 flavors as an ion, either a +2 charged ion or a +3 charged ion. Manganese, on the other hand, has a tendency to form 3 different types of ions. Manganese 2, which has a +2 charge, manganese 3, which has a +3 charge, and manganese 4, which has a +4 charge. Now we're getting into the nomenclature, naming things and figuring out how we write formulas and all of that. So this is where it's going to get really nitty-gritty. This is going to be stuff you'll work on next week probably, but if you start working on it earlier, you'll start to see this is a little bit challenging. This will get, historically, is difficult for people. Notice for the manganese, Mn, that there are Roman numerals written after the name of the element. Manganese 2. Those are the charges. So the Roman numeral 2 is +2. Roman numeral 3 is +3. Roman numeral 4, IV, is +4. Here in table 2.2 are some common monatomic ions found in nature. Aluminum tends to be +3, not +2 or +1, not -1 or -2, but +3. Barium tends to be +2. So if you go back and look at the table, there's a pattern here. One pattern is, or there's several patterns I should say, one is the first column on the left, column 1A. those metals tend to lose one electron and have a charge of +1. You should memorize that. The second column, they have a tendency to lose 2 electrons and become +2. Memorize that. If you go all the way over to the right to 7A, so that's group 7A, F minus, Cl minus, Br minus, I minus, they have a tendency, those elements tend to gain an electron and become -1. Coming over to the left, group 6A, they have a tendency to gain 2 electrons and become -2. And then there's not much more to patterns there, but those are the ones that you should remember. The first, group 1, group 2, and then finally group 6A and 7A. So there's 4 groups you should remember. Okay, so you don't need to memorize all of the ions in table 2.2, but I would look them over, take a look, see if they make sense. Table 2.3 are what are called polyatomic ions. So these are ions that are comprised of more than one atom. So for example, ammonium, NH4+. It's an ion because it's charged. It's a cation because it's positively charged. It's a polyatomic ion because it's more than one atom. These exist in nature. NH4+. H3O+ is called hydronium. Hg2+ is called mercury 1. There are many more anions than there are cations for polyatomic ions. Acetate, azide, carbonate, these are all some common ions. Those are all polyatomic ions. What comes up next is how you write formulas from the ions. So this will be a task for you to learn how to do. So you really want to read through here very, very carefully. Aluminum and oxygen is shown as an example. Aluminum has a charge of +3. Let's check that. Aluminum, oops, let's come all the way up here. Aluminum's +3. Oxide, -2, down at the bottom of the anions there in table 2.2. Those ions combine in small ratios. The ratios they combine in are such that the charge is neutralized. Aluminum has 3 positive charges. Oxygen only has 2 negatives. So they cannot combine in a 1-to-1 ratio because 3 does not balance 2. So what happens is you take multiple numbers of the atoms or the ions. If you take 2 aluminums, that gives you a total charge of +6. If you take 3 oxygens, that gives you a total charge of -6. So they show you here a little quick way to figure it out. If you have 2 ions with different charges, meaning one is +3 and the other one's -2, switch the numbers. The 3 goes behind the oxygen and the 2 goes behind the aluminum. So you take the charge of one ion and write it as a subscript for the other ion. And then combine those 2 ions together and you have what's called a chemical formula. Al2O3 is a chemical formula. It shows the combination of aluminum and oxide ions to form a compound. Then you go through naming ionic compounds. So you're going to go through these rules. They're going to tell you how to name ionic compounds. You're going to practice them. Practice as many of those ionic compounds as you can. You may have noticed that in the syllabus, I listed a lot of end-of-chapter problems for this section because I really wanted you to get some practice naming ionic compounds. It gives people a difficult time, so I wanted you to be able to do that. The next section, 2.7, is what we call molecules and molecular compounds. These are not charged ions. These are not ions at all. They don't have electrical charges. They're neutral. So for example, CO, carbon monoxide, is right in here in the middle with the black and the red one. That's called a heteronuclear diatomic. That's representing carbon monoxide. It's a neutral molecule, but it's a compound. And so read through here again. This is going to talk to you about how to name certain types of compounds. In particular, pay attention to table 2.4. Pay attention to table 2.5. That's the information you need to be able to name these compounds. It's actually much easier to do molecular compound naming in this section than it was in the ionic compound section in the previous section. So do the sample problems here. And the practice problems here, these in table 2.6 are some simple acids. I would memorize those. HF is hydrogen fluoride or hydrofluoric acid. So these are 5 common acids. I would memorize those formulas. And then there's a little bit of naming here for naming acids. Table 2.7, I wouldn't worry too much about that. That's in here. You can read over it, but we do not expect you to be naming organic compounds in this course right now. All we're really focused on is naming the molecular compounds that are listed through the simple acids, and then the ionic compounds, which was in the previous section. So you don't need to do table 2.7. You don't need to do table 2.8. You really don't even need to worry about table 2.9. Read it over, but it's not a big issue. So in a sense, your last sample problem that you would really focus on is 2.10, not 2.11, and then go through some of the checkpoints there. Do checkpoint 2.7.1, 2.7.3, and 2.7.4. You can do those ones as well. Okay, so that's just a brief overview, just to give you an idea of what to work on. The next chapter we're going to work on is 3. That's coming up, but that's not going to come for a little while. So good luck. What I will do is I will start to do some Alex problems this week for chapter 2 to give you some practice with that, and then we'll move forward from there.